Welcome to New Energy Conversations with Early Career Energy Researchers. My name is Megan, and I am the Manager of Academic Initiatives at the Irving Institute for Energy and Society at Dartmouth College. And I am very excited to welcome everyone here today to kick off our fall season of the New Energy series. So this series began during the pandemic as a way for up-and-coming energy and climate scholars to stay connected with each other and share their work. And since then, we've hosted almost 50 speakers, and the series has since then sparked an event, which is the New Energy Summer Summit, which just completed its second year. And this brings together a really highly multidisciplinary cohort of early career energy and climate researchers to the Dartmouth campus to forge new connections and potential collaborations. And both our speaker and our moderator have attended the New Energy Summit, so we're really excited to have them back. And we'll introduce our speaker and our moderator in just a moment. And after our speaker shares a presentation with us, we'll have a chance for a discussion and Q&A. So please feel free to enter any questions that you have for the speaker at any point during the presentation. And you can do that using the Q&A icon at the bottom of your Zoom screen. And so now I will kick us off by introducing our moderator for the talk, June Lukuyu. So June is an assistant professor of electrical and computer engineering, and she's affiliated with the University of Washington Clean Energy Institute, and she is also a fellow of the Energy for Growth Hub. She also directs the interdisciplinary Energy Analytics for Society, or IDEAS, research group, which focuses on developing and planning sustainable, inclusive, and integrated energy systems and technologies for underserved communities, centering on promoting social development and human empowerment. June earned her PhD in electrical and computer engineering from the University of Massachusetts Amherst, and prior to that, she earned her MSc in renewable energy systems technologies from Loughborough University, and her BS is in engineering science from Smith College. June employs a multidisciplinary approach incorporating data analytics, computational techniques, energy system modeling, and social science methods to develop comprehensive models for integrated community energy development and planning. Her research emphasizes the importance of meaningful community engagement and participation in the planning process, recognizing that sustainable and inclusive energy solutions are most effective when developed collaboratively and with the active involvement of the communities they serve. So we're very excited to have June here. She's given a talk in this series before, so we're really excited to have her back as a moderator. So welcome, June. I'll turn it over to you.
Thank you so much, Megan. Thank you so much. It's really great to be back. And it's my pleasure to introduce you all to Renee Obringer. Renee currently serves as an assistant professor in the John and Willie Leon Family Department of Energy and Mineral Engineering at Penn State University. And at Penn State, she's also affiliated with the Earth and Environmental Systems Institute and the Institute for Computational and Data Sciences. Renee's research aims to better understand the impact of climate change on energy systems by leveraging data analytics and other computational techniques. And prior to working at Penn State, she was a postdoctoral fellow at the National Socio-Environmental Synthesis Center, during which she sought to better understand the connection between water conservation attitudes and anthropogenic droughts in the Colorado River Basin. She obtained her PhD from Purdue University in environmental and ecological engineering, and her dissertation focused on evaluating the impact of climate change on urban water resources. Also, while she was at Purdue, she was affiliated with the Ecological Science and Engineering Interdisciplinary Graduate Program, and she holds a bachelor's degree in environmental engineering from Ohio State University. Personally, I'm really excited for this talk, and so with that, I will hand over to Renee to give her talk. And just a reminder, please drop your questions in the chat and Q&A, and we'll get to those at the end of the talk. Thanks. Over to you, Renee.
All right. Thank you, June, for that introduction. Just going to share my screen here. All right. And let me make sure I can see things. All right, so as June introduced, I am Renee Obringer. I'm at Penn State, but my research looks into the impact of climate change on urban systems, specifically energy and occasionally water. And in particular, I leverage what I call domain-informed machine learning. And so that's really a type of machine learning that is emphasizing the use of domain knowledge to improve the prediction as well as improve the interpretation, so that we're not just dealing with these black box models that nobody can really understand. And so today I'm going to be talking about a couple studies in which I looked into the impact of climate change on electricity demand, in particular, across the US. So to give you a brief outline, I'll start with just some very brief background on why I do this, but also how I do it, and then get into two studies, one focusing on the water electricity demand nexus, and the other on air conditioning use in particular. So the motivation for this work really stems from, the ongoing climate crisis and the projections that the IPCC has been making for years now. And on here are the most recent projections from the IPCC 6, I believe. And so down here, we've got our best case scenario, and up here, we've got our worst case scenario. And what I try to do in my work is take these scenarios and sort of apply them to local problems or local systems to see how this sort of larger global climate crisis might impact smaller communities at the city or even household level. And so to do this, I leverage what I earlier mentioned, domain-informed machine learning. It's sort of a subset of what is known as predictive modeling or supervised learning. And this is just a tree to show the breadth of what we could consider machine learning or predictive modeling. We've got everything from more simplistic linear regression up to more complex neural networks and getting into deep learning and artificial intelligence. In particular, where I tend to focus is in this area here. And so we have decision trees, we've got ensemble of trees, and in particular, I focus on these large ensemble of tree methods that allow me to do a little bit more interpretation than I could in a deep learning framework, but also have very robust predictive capabilities. And we can talk more about this after if anyone is interested. But to sort of break out the process that I go through when leveraging these methods, it starts with data collection. And within that, I need a response variable and a set of predictor variables. So the response is what I'm trying to predict, in this case, electricity demand. And the predictors are what I'm using to make that prediction. There's often some pre-processing to get to the final data set. But the bulk of the model happens in this green box here, where I train the model on observations. I test it on a data set that was held out and previously used, measure performance, maybe select a model, maybe select a variable. And then I repeat that so that I'm within this cross-validation framework. And this is really where the method allows you to sort of stabilize and do some testing to see how well it's doing at predicting rather than just explaining what we see in the data. And then the inferencing and analysis is where sort of those implications come from, where I look at, how will climate change impact electricity demand and what does that mean for our systems? So the first study I'm going to talk about is really a culmination of 3 primary papers. The first came out in Applied Energy, the second in Climatic Change, and the third is now available on arXiv and hopefully will be accepted for publication soon. It's sort of under that weird final editing stage. But primarily we'll focus on work from these 2 papers here. And so the research question within this water electricity nexus study was looking at how climate change would affect the coupled water and electricity demand for urban residents across the US. So looking at the simultaneous use of water and electricity and how those 2 demand structures may co-evolve under climate change. And so to show you, sort of demonstrate how my methods work, my goal is to ultimately project these demand structures into the future. So I start with my data collection. I've got some weather and climate data, observed water demand, observed electricity demand. And I start with those observed values, run it through my machine learning framework, and the output is this coupled prediction of water and electricity demand. And I can still compare that to the original, to the raw data, to see how well my model is doing. If we have a high enough predictive accuracy, we move on to the projection step, in which case I replace this observed weather and climate data with the simulated CMIP5 in this case, and future iterations would be CMIP6 set of models. In particular, I tend to lean towards RCP 2.6 and RCP 8.5 to give me that breadth of possibilities going forward, the best case scenario and the worst case scenario. And one key difference here is that because I'm working on a projection mode, I don't actually have a means to test how accurate these projections are. We're just sort of going based off of how accurate our predictions were in the observational space and saying, well, we feel confident that this relationship is accurate. And so our projections are always then compared back to that original prediction. And in particular, I do these analyses on temperature-based thresholds generally. So instead of looking at what might happen in the year 2030 or the year 2045, I look at what might happen after 1.5 degrees of warming, after 2 degrees of warming. And this sort of both grounds that research within the IPCC framework, as well as the international governance on discussing whether or not we're going to stick to 1.5 or 2 or go further. But it also allows for a little bit more fluid analysis instead of being like super prescriptive and saying this is what the model shows in 2030. It's saying when we hit 1.5 degrees, this is what's likely going to happen based off our models. And so to jump into the results, so here I have, I'm showing the relative changes for just Chicago. So as I mentioned, we did this analysis across many US cities. In particular, in the climatic change paper, we did this analysis for the Midwest as a whole and specific cities in the Midwest, but Chicago being the largest, I present that here. And so we've got 2 temperature thresholds, our 1.5 and our 2 degree threshold. They're upcoming. And then we've got electricity and we've got water. And so we're seeing how these 2 demands might change under these 2 temperature thresholds. So we can see that electricity under 1.5 degrees, about 12%, under 2 degrees, about 20% on a per capita basis, with some pretty large error bars because we are dealing with future climate simulations and no one simulation gives the same results. So that's what these error bars are showing. With water, we're seeing less of a change. So under 5% for both temperature thresholds, with actually a lot more errors, some models predicting that there could be a reduction in water. And this is largely because, well, we think it's because Chicago being more urban, there isn't a lot of outdoor landscaping on like a per capita basis. And so we wouldn't necessarily see that climate impact showing changes in water, except on sort of the outskirts where it becomes more suburban. And we see this pattern across a lot of the US when we, what I'll show in a few slides, that the larger cities tend to show less changes in water, most likely because they are so urban, there's just not that climate impact. But if we focus in on this electricity use, we can see that, as I said, after 1.5 degrees, that's 12% per person. What does that really mean in terms of the city's electricity supply? Based off of what Chicago residents currently use on average, this would essentially mean that the city would have to supply at least 745,000 megawatt hours in a given summer month on top of any existing population growth, etc., than what they supply now. And this is a huge number. To put this in perspective, In New Hampshire, the average household will use about 920 kilowatt hours per month. If we go through and do the math, this level of megawatt hourage would power every single household in New Hampshire for 1.5 months. And this is the level that just the city of Chicago will have to further supply due to the climate change, leading to changes in electricity use. And then if we look at 2 degrees, we see that that nearly doubles into 16 or 1,600,000 megawatt hours. And again, this amount of electricity would power every household in New Hampshire for over 3 months. And this is what our models are projecting the city, or rather the utility that serves the city, will have to supply due to climate change alone. So if their population grows, if technology changes, if cultures shift towards higher usage, that number could increase even more. And this has significant impacts on how we think about grid management, especially when we think about trying to transition and decarbonize the energy system as a whole. Are our grids, are our utilities, are our management agencies accounting for these possible significant increases? Because if they aren't, then we might have to fall back on fossil fuels. We might, in worst case scenario, experience supply inadequacies and blackouts. And so this really has a lot of implications, for how we manage our systems. And so once we had this sort of model up and running, what we did was we expanded it to the entire US. And so we started with 6 Midwestern cities. We expanded it to 46 major cities across the US. And at that point, collecting all of the observation data, running all the GCMs, downscaling them, bias correcting, became quite arduous. And we thought that, while we as academics had the computational resources to do this, a small community, even a major city in the US, might not have those same computational resources or expertise. So we started to look around for proxies of the traditional GCM data sets for future climate projections. And we found these climate analogs. And so here I'm showing the cities of interest, so our US cities, and they're most likely climate analog under RCP 8.5 after 2 degrees of warming. And so we can see that we've got Boston here, and they're sort of going down somewhere around DC. New York is going to Arkansas. And essentially what this is saying is that under this future warming, the average climate of New York City, for example, will feel like the current climate in northern Arkansas. Miami, the climate in the future will feel like the current climate of southern Mexico. And the climate analog approach has 2 benefits. The big one for us and for people that might be using similar models is that you don't have to run the GCMs yourself. You can figure out what these analogs are. The paper that we obtained these from had 540 North American cities that they did the analysis for. There are other people doing them for Europe and for Africa right now. And so you can find these analogs, and then you just need to get the current weather in the analog, or the current climate in the analog, and input it into the model, which is what we did here. And so to look at the results, here we have the percent change in summer per capita electricity demand across our 46 cities. These bubbles are sized to the population. So New York, quite big, Chicago, LA. And so we can see that most of the cities are projected to experience increases upwards of 20% in their per capita electricity demand. But we do have a few cities that are actually slated to experience less. And this in and of itself is a bit of a, surprising result. But what we found is that these cities, if we look back at their analogs, are almost always having average analogs that are in Mexico, but also in some of the more tropical areas of Mexico along the Gulf Coast, in the Gulf of California over here. And what these analogs have, their current climate tends to be slightly cooler in terms of experienced temperature, as well as experiencing more precipitation than what some of our cities in the southern US currently experience. And so what we're seeing is this impact of a potentially novel climate leading to possible reductions in electricity use in some states. And it is interesting that there is sort of this gradient here almost, where we've got some of the northern cities experiencing these extreme increases and some of the southern cities experiencing these slight decreases, which again has implications for how we manage the larger grid if we've got certain ISOs and certain regions experiencing difficulties keeping up with demand, while others are maybe experiencing difficulties of having to curtail and lose some of that electricity that they've generated from various technologies. And this is only for the summer months. If we look at the winter, we see almost the opposite. So almost every single city in our analysis is showing a decrease in winter electricity. There are some cities in the south again that are showing these increases, and these southern cities are likely already using, primarily air conditioning as our sort of climate-driven electricity use in the winter time. And so by getting, their changes, they are sort of increasing it. But we're seeing these like extreme decreases, probably due to the lack of heating need as we get warmer and warmer. And this, when we compare these two, begins to give more implications. So we already have issues of, the cities requiring more electricity in the summer. Where are they generating that from? How are they accounting for that? But if they need even less in the winter, then we're going to have these continuous mismatching, because we can't just turn on a power plant for the summer and turn it off for the winter. That takes a lot of effort and they don't like to do it. They want to keep them running. For the most part, they can turn down and turn up, but they want to keep it on for the whole year. And this sort of very sharp change between the seasons could pose a significant issue for maintaining a grid without having to shut down and bring back on. And it also represents an opportunity for having more renewables, which do have that benefit of being able to sort of produce more when we need them to, and storage capabilities as well. But in general, thinking about how we manage our grid and what we are going to do with these possible electricity changes is something that my research is sort of going towards, and looking more on those implications, because it's one thing to say, the models are showing these changes. It's another to say, are we accounting for them? And if not, what do we need to do in order to account for them? All right, so that's the water energy nexus side. The next study sort of builds off of that, but instead of looking at the city level, we downscaled even further to try to understand how households were changing. And this article was published in Earth's Future about a year and a half ago. But essentially our question, very similar to the last one, was how will climate change impact household level air conditioning use across the United States? So again, we're trying to look at the entire US, because that allows us to look at these patterns from state to state, but it also sort of broadens our ability to do implication-based analysis. And so to quickly go over those methods again. So here our goal is to project air conditioning use. So I've collected, again, the climate data that I'm using to sort of estimate that relationship between, in this case, air conditioning use and climate. And I've got my air conditioning use data that was collected via the Energy Information Administration's REX survey. And so it's not a household by household, it's sort of a statistically representative household for a given state. And we run it through the machine learning model. And in this case, because we're only looking at air conditioning, our output is only a prediction of air conditioning. And then, like before, I substitute in from the observed climate data to the projected climate data. And here, I'm only going to show what happens under RCP 8.5, just for simplicity's sake. But again, we did do temperature thresholds 1.5 and 2 degrees. In this case, we held off from doing the 3-degree threshold because it pushes us pretty far out past our planning horizon in terms of how we manage grids. And so we didn't want to go too far out. So we wanted to stick between 1.5 and 2, which sort of puts us about 2050, 2060 for 2 degrees of warming under the current trajectory. So the results, the primary result is shown here. And essentially what we're seeing is that the background is showing the baseline kilowatt hours consumed for air conditioning use. And then the bars are showing that 1.5 and 2 degree % increase. And so New Hampshire's over here, they're actually connected in to the rest of sort of New England in the Northeast. But under 1.5 degrees, expected to see 5.4% increase in per capita air conditioning use, and 9.4 under 2 degrees. And this for, the Northeast and this particular region could be quite big for their grid, which is currently not very, has some of the lowest air conditioning penetration in the country alongside the Pacific Northwest and parts of California. And so when we start to see these increases in uptake of air conditioning use in areas that previously hadn't had that or needed air conditioning use, then it sort of adds this additional burden to our system that we're not only keeping up with the change in demand, but we're also keeping up with changing patterns of demand where people that previously didn't use air conditioning are now using it all the time. And so then just some other sort of key areas. We have Arizona, which has some of the highest use of air conditioning in the country, unsurprisingly. We're seeing this 6% increase and then 9% increase. And then these differences between 1.5 and 2 degrees can be quite significant. Here in the Midwest, we're seeing some places almost a tripling in that % increase from about 4 to 13 for Indiana and Ohio. And so this change between 1.5 and 2 degrees will be absolutely critical. Like right now, most under 1.5 degrees, it could be bad, but it might be within range of the current grid to sort of handle that with their current planning process. But if suddenly we're almost tripling that increase between just a 0.5 degree of warming, that could provide a serious shock to the system if they're not prepared for that. And so across this, we sort of look at what is happening, and this is a statistically representative household. And so then within our writing and our paper, and I'm happy to talk about this more, we sort of delve into those implications of what this would mean for the average household across these states. And what we found is that some states that have very high poverty levels beyond the average of the country are also in places where their air conditioning use might increase quite a bit. And so we begin to talk about some of these social implications of, yes, the average household is expected to increase, but if we have more affluent people, they're more likely to have access to, be able to afford their energy bills for increased air conditioning, have access to cooler spaces regardless, may be able to move to a better climate, whereas the less affluent, disadvantaged communities are going to bear the brunt of these impacts, and sort of looking into what that means. And in terms of the future work building off of this, my lab is looking into energy poverty and what this might mean in terms of how energy poverty in this country as well as other countries might shift under a warming climate when we have sort of air conditioning use as our primary adaptation to extreme heat when we're forced to stay inside. And what does that mean for people who can't afford it or are unable to even obtain access to those cooler spaces? So with that, a little under time, but that's not bad. Thank you for attending the talk. This work has spanned my PhD, my postdoc, and now going into my faculty position. So there's lots of funding and collaborators to be acknowledged, but happy to answer your questions now.
Thank you so much, Renee. Really captivating talk. I'll kick us off with some few questions from the audience. First question is, are the predictors of demand change in the winter or summer consistent with the current trends? For example, are there northern cities in the US experiencing decreases in energy demand due to climate change during the last couple of winter seasons? Have you considered that, or are these just solely based on kind of historical data moving forward? And have there been, maybe speak a little bit more about some of your results with the accuracy of your predictions?
Yeah, so let me pull up this slide. So this is for the Midwest in particular. So this is that climatic change paper. And essentially we've just got our summer and our winter, and we're showing electricity and water use and how they trend. The blue and green lines are just two separate variable sets that we were investigating. And so, but this is where we show sort of the accuracy of our model being with the root mean squared error here and summer and winter. And we do see those larger errors in the winter, which we have attributed to the fact that there's less of a climate sensitivity to our winter usage, particularly in places in this country where we use natural gas for heating instead, or pellets or wood instead of electricity. So electric heating is still not as big in this country as other forms. And so we see less of that climate sensitivity that we do in the summer. So there's no outdoor landscaping, air conditioning use is a huge thing. So we do see these larger errors because we're only giving it climate predictors. We're not accounting for population growth, technological changes, any of that. But nonetheless, we do still see these fairly accurate models. And the reason I bring up this slide as well is that this shows the observed data. And so we took data from 2000 to 2020 for these cities, and we sorted them. And so we can see that we've got some cities down here that have lower water and higher water across the summer, and similar for electricity. And we can see that our actual data is here in black, and our green, if you can see the green sort of dashed line there, is the final model that we did. The blue was a separate variable set, but we can see that it follows that trend fairly well in the observational space. And so going forward, we felt confident to use that relationship into the projections.
Thank you. I think just a quick follow-up on that. I think
Yeah.
a lot of what comes to mind with thinking about, accuracy of some predictive model is what is good enough or what is accurate enough. Are there any, threshold, or what do you measure? So is 0.8 good enough to use, or are you trying to get to a certain level or threshold of accuracy or error?
Yeah, so we weren't looking at trying to get to a certain threshold. We sort of just were trying to make it as best as it could be, which is why in this case we tested multiple variable sets. The specific model we're using, multivariate tree boosting, at the time was one of the sort of state-of-the-art multi-outcome machine learning models. So it allows for multiple response variables. So there wasn't a lot of room for doing model testing. Lately, there's been sort of an uptick of different models coming out that allow for these multiple response variables. So in the future, we hope to go back and sort of test some of these models out. So yeah, we were really just trying to get it as good as possible. And one of the key things we could do to see how well we were doing was look at different variable sets and do variable selection. And so this green one is our final model that includes relative humidity, wind speed, dew point temperature, dry bulb temperature, sort of these basic climate. And our blue model was just dry bulb temperature and precipitation. And we compare those two because in industry and government, most of the time where they're trying to estimate the climate sensitivity of their demand, they only look at precipitation and dry bulb temperature. But humans, when we actually go outside and judge what the temperature is, judge how we feel, we're accounting for a lot more than just what the thermometer says. We're also thinking, is the wind speed making it cooler? Is the humidity making it feel warmer? Things like that. So we find that when we include those additional variables and give our model that extra information, it does improve. But we weren't looking for a threshold, just trying to make it as good as possible.
I see. Thanks. And so could you speak a little bit about what variables and their granularity in the predicted climate data?
Yeah, let's see. I removed that slide. So what we initially did was we pulled down daily variables. So we had dry bulb temperature, dew point temperature, wet bulb temperature, humidity, wind speed, and precipitation. So 6 key climate weather variables. We extracted daily data, and then we aggregated them to monthly so that we had the average daily minimum, the average daily maximum, the average daily mean, the average daily average, for the temperature, humidity, and wind speed. And then we had total precipitation in the month and the number of days in which there were precipitation, so the number of wet days in a month. And that was done so that we had multiple measures of how the climate was affecting. So maybe minimum temperature is important in one, minimum, dry bulb, maximum dew point, things like that. But we also had monthly water and electricity values collected from the utilities. So we had to at least get month to month.
Great. And I think you mentioned that your data sets were public. Please correct me if I'm wrong. Were this robust enough, or do you think there were other data sets you could have leveraged that were not accessible that would have made your predictions better?
Yeah, so we feel pretty confident about our data set. So the electricity was collected from the Energy Information Administration through their sort of various surveys. And that goes through its own sort of checking process to make sure that it's accurate and there aren't any sort of weird outliers or misinputted error data, basically like a typo. So that's where we got the electricity, and then the water data we collected from actual local utilities through Freedom of Information Act requests. So we ended up submitting close to 90 FOIA requests across water utilities in the country, and ended up with only like the 46 that we included that had the full amount of data that we wanted, and were able to provide it with minimal cost. And so that data itself does have the possibility of having some user inputted error, but we did sort of run through and make sure that there weren't any extreme outliers and that the patterns sort of matched with each other, instead of having like a city in which case there was suddenly like a tripling of the water usage in one day or something that could indicate that maybe there was a typo, or even if it wasn't a typo, that was some sort of leak or something. So we did do like a sort of a check there. But yeah, getting water and electricity demand data can be very difficult. And I think that having access to like utility data is probably the best that we could do at this time.
Awesome. I'll take us back to the discussion of the analog cities. A couple of questions about that. Do they in any way match the target cities in, say, demographics or economic or energy resources, or are they just solely on climate conditions? And also, what are those climate factors that were included in selecting the analog cities?
Yeah, so they're only climate. So there's no accounting for demographics or culture or anything. It's solely this city will experience this, likely to experience this climate of another city in the future. And in order to obtain these analogs, I will say that this wasn't our study to get the analogs. This was a study by Fitzpatrick and Dunn in 2019 Nature Communications paper, which I'm happy to find and link below. But what they did was they took 4 variables, so precipitation, total monthly precipitation, monthly min, mean, and max of temperature. And they did that across the 4 climatological seasons to get sort of this 12 key variables. And through a statistical analysis determined that based off of these 4 variables across all the seasons, this city is the most likely for this sort of other target city. And they sort of have these nice heat maps that they show as you get out from that city, it becomes less and less likely. So they did sort of a similarity measure in that regard.
Great. There's also a question about how you quantify the impacts of climate change on electricity demand, specifically, especially during heat wave events.
That's a great question. So we only do the average for now. And that's primarily because it's just the data that we had was sort of these total electricity, but like average climate events. And so what essentially we do is we take the relationship between the electricity use data. We first detrend the electricity use so that we're focusing solely on the climate impacts. And so we take that detrending data, and then we use the machine learning model to figure out what the relationship is between the combination of our climate variables and our detrended electricity and, in this, often water use coupled. And then we use that relationship. We make an assumption that the relationship is going to be stationary into the near future. And then we use that to see, okay, if we now have different input variables with that same relationship, how does our output change?
Great, thanks. Another question around the projected increase in AC use. Does that include estimations of households that don't own ACs but are expected to acquire one in future? And then are the values in the mini bar plots on the map percentages per capita?
Yes. So I'll answer the second question. These are percentages per capita. So you can, or per average household. So here, Virginia, the average household, our model is showing that they would increase their electricity use for air conditioning by 7.4% under 1.5 degrees and 10.5% under 2 degrees. And this is just for households currently using air conditioning. So we didn't account for increased penetration of air conditioning use, which makes seeing places like the Northeast having increased for current users. It would likely become even higher if they're seeing a high penetration. But it's also why we suspect that we're seeing such low values in the Pacific Northwest right now. Because when we did this study, they had very, very low air conditioning penetration. Then we did the study, we see this low, then they had that massive heat wave and their air conditioning penetration has like skyrocketed in the last couple of years. So if we ever redo the study, I would suspect that we would see higher changes for Oregon and Washington because there would be a higher sort of use of air conditioning that we can pull out that exact climate relationship.
Great. Just a follow-up question on that. One is, could you then speak about any other limitations in some of your models, including not having as up-to-date data, and how you think you would be able to address that in future?
Yeah, I think sort of the big limitation for a lot of this work is that we are making an assumption that the relationship is going to be stationary. And that is sort of a challenge across all machine learning type of models, is that it's very rigid in that we train, it learns a certain relationship, and then it uses that in the future. And so if that relationship changes, then we don't know. It's one of the big unknowns. And in order to do that model, we sort of have to make that assumption. There are because everybody is sort of aware that it is a challenge within our community, there are a lot of people who are working on means to improve this, to essentially reduce the uncertainty around knowing whether or not that relationship will be stationary or not. And so that's a pretty interesting area of work, but it is a limitation. And then, of course, this study used data from 2018. And so as we continue to collect data and get more and more, as well as sort of as climate change progresses, we're going to have more information about how that relationship is now and how it might look in the future. And so I think that would definitely help strengthen, just collecting more data. And there is a lot of work going into building these sort of reinforcement learning based models for climate change impact assessment, because you can pull in this last year's data and update the model, get a better understanding about how things are changing, and then use that to make projections going forward.
Absolutely. Does your model take into account the percentage of AC load that is met with electricity from rooftop solar panels or just from the grid with net metering?
No, so it doesn't. It's just looking at straight usage based off of the reporting that was done through the REX survey that had 20,000 households across the US. And so using that sort of reported, this is how much air conditioning was used, and trying to figure out that climate relationship. If, as rooftop solar can be used for air conditioning, then that sort of reduces how much they're still using that electricity, but it's not going through the grid. But they would still effectively be using more or using the same amount of air conditioning. They're just, it has different implications for how we manage our grid. That, you know, if rooftop solar can take on some of that increased load, that means that our grid is freed up to do other things and might not run into some of those negative consequences with surging air conditioning use.
Great. I'm so glad you kind of mentioned future area of kind of potential interest looking at those social implications, you know, thinking about energy poverty. I'm curious, what do you think, like, do you think we'll ever get to the point where these big models can take into account this, you know, granular equity issues? For example, we've seen studies before that talk about energy limiting behavior of people who access AC, or even in the case of water, we see wealthier neighborhoods, you know, being able to use more water, to, especially in California. So what would it take to get, you know, large scale models to take into account those very granular accounts of energy equity?
Yeah, I think it would be very difficult to integrate some of those measures into a model, because a lot of stuff can't be quantified in the sense that these machine learning models expect their variables to be. So there's, I think that the opportunities come from like really good collaborations, and some of my more successful sort of collaborations with social scientists on sort of that social side have come from, you know, from the interpretation phase. And so we developed a model to predict water consumption at a census tract level, and sort of noticed that some of the census tracts were like wildly over predicting their water consumption. And we did like a really nice social science interview study in those census tracts, and found that these census tracts, like the neighborhoods in the census tract, had really good sort of neighborhood organizational norms, and were very sort of pro-environment compared to the rest of the city. And they were talking about, yeah, we all have rain barrels. We never water our yard. Like, it's just dying in the summer if we don't get rain, sort of thing. And I thought I think that was a very sort of rich means to integrate that and to sort of start to understand these social implications, that it's not that we're trying to have a machine learning model predict the social implications, rather we're taking that social knowledge and applying it and saying, this is why we're seeing that, and what does that mean for, you know, going forward.
Great. And just one last question. You talked about moving forward, kind of focusing more on implications work. Are you going to be focusing more on thinking about implications on, you know, behavior or policy or infrastructure or supply, or a mix of all?
Yeah. Probably a mix. So I think we're sort of focusing more on the infrastructure implications, as well as sort of the localized social community-based implications. And so when we think about sort of this air conditioning use at a household level, sort of my goal is to take, in sort of a broad sense, is to take these really large scale global climate models, and the global climate, you know, crisis, and downscale it into tangible impacts for communities, so that they can take that and, you know, make adaptation plans for themselves and sort of learn and communicate those results, so that it's not just some abstract, the temperature has increased 1.5 degrees above pre-industrial levels sort of thing. It's tangible that, you know, your household air conditioning use is likely to increase. Your family, your friends, your neighborhood, your community is going to be experiencing this. You know, there are things that we can do to then sort of make that easier. So it's more in the adaptation space. And sort of some of that is for infrastructure, thinking about the grid and all of that. But a lot of it is also into sort of community-based action and decisions, that this is what sort of bringing it down to a level that is more digestible for, you know, non-climate scientists.
That's perfect. Do you have any last thoughts, or I feel like that feels like a last thought, but
yeah, I think that's a good last thought. It really is sort of what I am trying to do. And I think that, you know, using machine learning in this way that is sort of interpretable and computationally efficient and flexible is a great approach for sort of taking that downscaled community-based view, because it can sort of function very quickly at lower levels than having these large climate impact assessment models that are very good at what they do, but might not be accessible to everybody. And so trying to bring that down, and you know, I think it's a really powerful tool to do climate change impact assessment.
Great. Thank you so much, Renee. I wish you all the best with. I'm looking forward to actually seeing more work that comes out of this, and I've really enjoyed your talk. Yeah, over to you, Megan.
Thank you so much, Renee. Thank you so much for a wonderful talk. That was really, really interesting. And June, thank you so much for moderating a really fantastic conversation afterwards. It's been so wonderful to have you both here. We really appreciate it. So with that, we'll close the session, and thank you again to Renee and to June for being here. We have a couple of more new energy talks coming up this fall. On October 18th, we have Shell Lyons from Australian National University, who's going to be talking about public green banks and the transition to net zero emissions. And then on November 8th, we'll have Camilo Stubenberg, who is from Cornell University, who's be talking about grid collapse and whether that accelerates the energy transition in Lebanon. So very excited for those. Please tune into those. You can register at the link below, dartgo.org/new energy. And if you're here on the Dartmouth campus, or you will be this fall, please join us for Dartmouth Climate and Energy Week. We have a lot of different events going on for students, for members of the Dartmouth community, one or two of which will be live streamed if you're not here on the Dartmouth campus. So please check out what's going on for that week-long event at dartgo.org/CEW23. And we hope to see you at the next New Energy Talk. Thank you so much. And thank you again to Renee and June, and we'll see you next time.